On circuit analysis, we are studying transient circuits, and before this lecture, we have studied transient analysis of series RC and series RL circuit for a DC source in the presence of a switch that was closed at a time t is equal to 0. And we computed different quantities like current and voltage drop across different elements for all values of t. In this lecture, we will solve an example involving a two-way switch that is connected to position 1 for a very long time, and at time t is equal to 0 this switch is moved to position 2, and then we have to compute I2 of t for all values of t, right? Switch K remained in position 1 for a very long time unless the circuit achieved steady state. We know that a capacitor is initially a short circuit for a suddenly applied DC input, but it gradually develops voltage drop across it and is finally charged at a voltage equal to the supply voltage. So if the switch K remained in position 1 for a very long time, this means it gave enough time for this capacitor to charge itself to a voltage V. So when the switch was moved to position 2, we will find the capacitor in a condition that it is charged at a voltage V, capital V. So it is a charged capacitor having voltage V across it. So, and we have to find I2 of t for all values of t then, right? So let's analyze this circuit for different values of t first. Time t is equal to 0 minus, this means just before we moved the switch from position 1 to position 2. So at that time, the capacitor would have been charged at a voltage equal to V volt, and there would be no current in this path. In this path, there will be no current. So the capacitor was charged, and once it is charged, it is open circuited, and the whole applied voltage, capital V, appears across it. So Vc of t is equal to the capital V, the supplied voltage, because it is charged. It has been given enough time to charge itself to the supply voltage equal to the supply voltage. And then what happens at time t is equal to 0 plus? This means that after we have moved the switch in this position, then we'll have a charged capacitor charged at a voltage V and this R2 in the circuit. And we have to find this I2 of t, the current flowing through this resistor R2 for all values of t. So what happens at time t is equal to 0 plus, just after we have moved the switch to position 2. So for that, it's a charge capacitor, and we can have a sudden change in current through R2 because it is resistor. It doesn't oppose any sudden flow of current or sudden appearance of a voltage across it. So there will be a, a current V2 over R because this charge capacitor, it acts like a voltage source for a shorter period of time. So just after we have moved the switch from position 1 to position 2, it seems that a voltage source having value V appears across R2 because it's charge capacitor, and charge capacitor acts like a voltage source for a short period of time. So Vc of 0 plus and Vc of 0 minus is the same because the voltage drop across capacitor cannot change all of a sudden. Therefore, it remains the same, is equal to V, Vc at 0 minus. So Vc at 0 plus is the same as it was at 0 minus, that is capital V equal to the supply voltage. What happens at t is equal to infinity? It keeps on discharging itself. The capacitor keeps on discharging itself unless it has discharged itself and the whole energy across it has been dissipated as a heat in the resistor R2, and finally we have no current in the circuit, no voltage drop across capacitor, and no voltage drop across resistor because everything has been dissipated. because this source was a temporary source. It was charged at a voltage V, but since it is not a permanent source, it discharged itself by causing a current flow through R2. So let's compute the expression for I2 of t, this one, for all values of t once we have written these initial conditions 0 minus, 0 plus, and final condition infinity. So now we are ready to apply. What would we apply? We'll apply KVL, assuming a current I2 of t flowing through the series circuit. We apply KVL, Kirchhoff's voltage law, the expression to find voltage drop across capacitor plus the voltage drop across resistor. And this expression is from minus infinity to t. So it can be broken down into minus infinity to 0 and then from 0 to t. This refers to the initial voltage on the capacitor plates. This initial voltage, we know it is capital V, because it is initially charged at capital V. And since the polarity of V of this initial charge is of this initial voltage is opposite to what we have assumed, so we'll put a minus here. So plus this and plus this one, r di by dt. So we have computed d by dt on both sides of the equation, and then we are left with this equation. This is a homogeneous first order differential equation for which the general solution is this k1 plus k2 e to the minus t over tau. And now we have three unknowns k1, k2, and tau, which we can compute by putting initial value, the final value. By putting initial value, we get this expression. By putting the final value, we get k1 is equal to 0. This means k2 is v over r. So now we are left with only one variable. There was this one, tau. This one, tau. So how to compute tau? We'll put this I2 of t that we have just computed by after we have evaluated k1 and k2. We'll put it in equation A. What is equation A? This one, the initial equation for which we assumed this general solution. So we'll put I2 of t here, and we'll compute our derivative, and then we'll put I2 of t here. We'll keep on solving unless it's a simple linear equation, unless we reach to this point. 1 over tau is 1 over c. This means tau is rc. So rc, we have computed the final unknown tau, and I2 of t is then v over r e to the minus t over rc. So it seems it's a decreasing, it can be seen that it is a decreasing exponential having maximum value v over r, decreases with time. As the time approaches infinity, it becomes 0, because this capacitor isn't a permanent source. A charge capacitor works like a temporary voltage source. Its voltage drop decreases with time unless the voltage supplied by the capacitor is decreased to 0. So this discharge would be a decreasing exponential. So here's a small homework for students, that they are required to compute Vc of t for all values of t in this circuit. Vc of t. So we have computed I2 of t. So the homework is that students are required to compute Vc of t for all t. Right. So this is all for this lecture. In our upcoming lectures, we will keep on studying more circuits about transient analysis. Thank you.